So this is section 2.5. All right, so like I said, we've talked about this in kind of a roundabout way. We really know the results already. We're just going to make it more formal. So to introduce us to this, I want to say that we have a polynomial. So let's say this polynomial is 3x to the fifth minus, just making this up, something like that. And just looking at this polynomial, what did we say? How many zeros does this polynomial have? 5. Because how do we know it's 5? The highest exponent is 5, so we know it has 5 zeros. Well, when we were using real numbers, sometimes we couldn't find all of those zeros, because some of the zeros could turn out to be complex numbers. But we know that we've known that there are 5 zeros, so we should be able to find 5 zeros. Well, just with the addition of I, that imaginary unit, the idea of complex numbers, now we're guaranteed that we can find all of those zeros, and that's what the fundamental theorem of algebra tells us. So we have some polynomial. F of x is a polynomial with degree n. So, and we want n to be greater than 0. So we don't want a 0-degree polynomial. We're not talking about negative exponents. All of our exponents are positive. So if f of x is a polynomial with degree n, the fundamental theorem of algebra tells us then f has at least 1 0 in the complex numbers. And on Friday, once I wrote this, I was thinking, I'll tell a math joke that has to do with this at least. Mathematicians like to use that phrase, at least. So we just said we know we have an idea this polynomial has 5 zeros. Why would the fundamental theorem of algebra tell us we have at least 1? What can happen with zeros? If we factor a polynomial, what can happen with the zeros? Couldn't I have something, this one obviously doesn't factor that way, but couldn't we have something like x minus 3 to the fifth? So we could have a repeated 0. We could have a 0 with some multiplicity. And if the multiplicity happens to be the same degree as our polynomial, then we just get one number. We count it 5 times, but it's really only one number. So that's where that at least comes from. There's at least 1. They could be repeated. So we could have repeated zeros. So that's why we say at least. Try to be as precise as we can in mathematics. So we know we have at least 1 0 in the complex numbers. No matter how gnarly, how ugly, how long, what the coefficients are, what these numbers are, we can find a 0 in the complex number system. And remember that real numbers are also complex numbers. Real numbers are inside the complex numbers. Real numbers are complex numbers with no imaginary part. Well, the way that we're going to use this, the really important part of the fundamental theorem of algebra, I think, and this is pretty amazing, is what we call the linear factor theorem. And we have used this when we can factor our polynomial with real numbers. But now we can factor any polynomial. So f of x is a polynomial again, and the degree is n. So we have this polynomial. Degree is n is greater than 0. What the linear factor theorem tells us is that f of x has exactly n linear factors and we can write f of x out as, we just write out all of our factors. A sub n, because we can have some number out in front, so a sub n is just some number, times x minus our first factor, times x minus our second factor, times dot dot dot, times x minus our last factor. Or sorry, our last, not our factor, these are our factors, these are our roots. So we can completely factor any polynomial, and C1, C2, Cn are complex roots. So combine the fundamental theorem of algebra with the idea that we can factor our polynomial, and it tells us that now that we have complex numbers, we can factor any polynomial. And we can factor it out completely like this, where C1, C2, Cn are our complex roots of our polynomial. So that's really the power of the fundamental theorem of algebra. That's kind of the big thing that it tells us, is that with the complex number system, any polynomial, no matter how ugly, no matter how big, I can factor it out like this. And it's kind of like the fundamental theorem of arithmetic, which tells us that any integer, no matter how big, I can factor as the product of primes. It's the exact same idea, but here with polynomials I have linear factors, and with the fundamental theorem of arithmetic I have prime factors. So they're similar ideas. And we use the fundamental theorem of arithmetic all the time when we try to factor things. The questions about what the fundamental theorem of algebra tells us. So just by adding that I to our number system, we get the ability to completely factor any polynomial. So what I want to do an example. I'm not going to go through the entire process because we know the process by now, but we'll talk about it. And then write our polynomial write it out in completely factored form. So let's look at f of x equals x to the fourth minus 3x to the third plus x minus 3. And we want to find all zeros, or I'll say all roots, and write out in completely factored form. So we're going to write out in factored form. All right, so we have some tools that we use to find our roots. So how are we going to start? How are we going to start this problem, Zachy? We want to find the roots of a polynomial. So what do we do? What are our tools that we've been talking about in this chapter? We want to do synthetic division, right? So how do we choose? We're going to do synthetic division, so that's the big picture. So how do we choose what we're going to do synthetic division with? What can we do, Marcus? Find our P's and Q's. So here's my P, here's my Q. And thankfully q is 1. So our possible rational roots are what for this polynomial? Plus or minus 1 and plus or minus 3. Since q is 1, all we have is the factors of this. So those are our possible rational roots. So what other tools do we have before we start doing things? What can we narrow down our choices a little bit by using what? Descartes' rule of signs. So let's use Descartes' rule of signs. How many sign changes do we have here? 3 sign changes. So that Descartes' rule of signs tells us we have how many possible positive real roots? 3 or 1 positive real zeros. We can do something for the negative zeros also, can't we? What do we do for the negative real zeros? F of minus x. And we count the sign changes of f of minus x. So f of minus x, how do we find f of minus x quickly and easily? Change the signs on the odd powers. So f of minus x is x to the 4th, plus 3x to the 3rd, minus x. The 3 doesn't change because it's not being multiplied by x. How many sign changes do we have here? 1. So what does Descartes' rule of signs tell us? 1 negative real zero. So if I were solving this problem, I would try to find that one negative one first. And then I wouldn't have to worry about the negative numbers at all. What's the easiest negative root to find? Negative 1. So we're going to test negative 1, f of negative 1. We plug that in there, what do we get? Is it 0? F of negative 1 turns out to be 0. I plug negative 1 in here and calculate, I get 0. There's my negative real 0. X equals negative 1. So I've already found the 1 negative real 0. I don't even have to worry about the negative ones anymore. What's the easiest positive one to test? 1. We plug that in, f of 1. Does that turn out to be 0? No. So I'm just going to say not equal 0. So what is left that's our positive rational 0? 3. I don't even have to do anything, and I figured out that it's 3. So x equals 3 is one of the positive real zeros. I haven't even done synthetic division yet. All right. Now how do I find the rest? Now I start doing synthetic division. I'm going to do synthetic division with x equals negative 1. What does that do to the... What do we know has to happen when I do synthetic division when x equals negative 1? The 0 is the remainder. The remainder is 0. And when I do synthetic division on this 4th degree polynomial, what am I left with? 3rd degree polynomial. What do I do next? Another synthetic division with x equals 3, because we know that's a 0. We know that we have to get a 0 remainder. I'm doing synthetic division with x equals 3. I'm doing that on a 3rd degree polynomial. So what do I end up left with? Second, a quadratic polynomial. I'm not going to go through the steps. We all know how to do the synthetic division now, hopefully. If you don't, make sure you figure that out before the test. When I do those two synthetic divisions, I'm left with x squared minus x plus 1. And we want that to equal 0. Does this factor? This does not factor. So what do we have to do? Quadratic formula. When I plug a equals 1, b equals negative 1, c equals 1 into the quadratic formula, I end up with x equals 1/2 plus or minus square root of 3 over 2 I. There are my other two zeros. So I've started by using my P's and Q's, Descartes' rule of signs, eliminate some possibilities, and then end up using the quadratic formula. Yes?
Can you leave it in that form?
Leave it
Can you just like leave it like that as the answer?
at x squared minus x plus 1. If the problem asks you to find all zeros, then we would have to go to here. If it asks us to factor into real factors, then we could leave it like this. Okay? So then if we wanted to write out our function in completely factored form, what I would do is write f of x equals, and I'm going to write out my parentheses. So what goes in the first parentheses? X plus 1. Second parentheses, x minus 3. Third parentheses, x minus one of these roots. 1/2 plus the square root of 3 over 2i. And in the fourth parentheses, x minus the other root. 1/2 minus square root of 3 over 2i. There's f in completely factored form. So if the problem asks you to write your polynomial in completely factored form, this is what you do. And in the one parentheses, you just put x minus whatever your root is. And here we have two roots, so we have x minus one of them, and then x minus the other. That's our completely factored form. Questions on that, on the procedure? It's the same procedure we've been using for a week and a half or so now. Find our possible roots, synthetic division, get down to a quadratic, either factor or use a quadratic formula. We can find all our roots. All right, looking at this polynomial, anybody see another way I could go about doing this? Factor by grouping. Who said that? Very nice. So, I'll write that in red. If you recognize that this was factor by grouping, how am I going to write my factors? Do you see how we would do it? I'm going to factor an x cubed out of this first pair, so I get x minus 3 plus 1 times x minus 3. So this factors as x cubed plus 1 times x minus 3. All right, so factor by grouping, this tells me that x equals 3 is a 0. And we get to the same place that we were here. Here I have x cubed plus 1 equals 0, or x cubed equals negative 1, or x equals the cubed root of negative 1. We know how to take the square root of negative 1, but we will learn how to take the cube roots of negative numbers. Looking at this equation, how many zeros should this equation have? How many roots should it have? 3. Well, what do we know one of them is? What's a cube root of negative 1? A real number. What number times itself 3 times gives you negative 1? Negative 1. Well, there's my other two. There's the same roots that I got here. Synthetic division. We will learn how to take the cube root of negative numbers and the fourth root of negative numbers and the fifth root of negative numbers a little later on. It turns out that this are the other two cube roots of negative 1. One is negative 1, and these are the other two. But we could get to the same place that we did with our P's and our Q's by doing factor by grouping. So questions on our process. Should be familiar by now. Find your possible roots. Test The easy ones by plugging in. Do synthetic division. You're looking for a zero remainder. Reduce the power of your polynomial by doing division until you get down to a quadratic, and then either factor or use a quadratic formula. It's kind of, it's very, what we're doing is very algorithmic, you kind of turn the crank over and over and over again to get these zeros. All right. A couple of other interesting things that come out of the fundamental theorem of algebra. Conjugate pairs. Now let's look back at our solution. I know we didn't go through, but when we did our quadratic formula, we always have the negative b plus or minus the square root. Well, that plus or minus generates, when we have a complex root, it generates a conjugate pair. 1/2 plus square root of 3 over 2i, 1/2 minus square root of 3 over 2i. That always happens. Always. The complex roots of a polynomial always occur in conjugate pairs. So this relates back to several things that we've talked about and several things we've known for years. When we use a quadratic formula, you get that plus or minus. When we have a imaginary square root, we get a plus or minus. That gives us a conjugate pair. And that always happens when we have a complex root. They always occur in conjugate pairs. So let's think back to Descartes' rule of signs. When we find the number of sign changes, what can we reduce the possible real zeros by when we have a certain number of sign changes? What do we count down by? 2's. 2's, because our roots appear in, our complex roots appear in complex conjugate pairs. So if we have 4 possible real roots and one of them happens to be complex, then its conjugate also has to be a root. So they always end up in pairs. So that's why we go down by 2. For every complex root, you get 2 each time. So that's why in Descartes' rule of signs we count down by 2's, because our roots always appear in conjugate pairs when they're complex roots. So the kind of question you might see, kinds of questions that you might see that have to do with conjugate pairs. This first one should be 3 points on a test. F of x has 3, 5, and if f has degree 4, what is the other root? So we have a 4th degree polynomial. We have 3 of the roots. How can we figure out the other root?
Look at the complex number.
Look at the complex number, find its conjugate. So x equals 3 minus 2i has to be a root. So if you have a list of roots of a polynomial and it says what are the other roots, look for the complex roots. They have to appear in conjugate pairs. Now the mistake that a lot of people make is they start changing signs on everything. It's only the complex roots and it's only conjugate pairs. So our fourth degree polynomial would have to have 3 minus 2i as a root of the fourth degree polynomial. What if the question asks us to then write out this polynomial? So it gives us these roots and it says write out the polynomial. How do we write out our polynomial? F of x equals. What can we do here? X minus, just set up our parentheses, x minus 3. X minus 5. X minus 3 plus 2i. X minus 3 minus 2i. There's our fourth degree polynomial. I'm not going to ask you to multiply these out. I might say I'll give you a little bit of extra credit if you do on a test. But if you write out that your fourth degree polynomial is this thing, I'm okay with that. Technically this isn't written as a polynomial, but this shows to me that you understand the idea, the connection between the roots and the factors. And that to me that's the important thing. You understand the connection between the roots and the factors. So there's my fourth degree polynomial. I can multiply that out and get some x to the fourth, something x to the third, etc., etc. All right, questions on that idea? So this gives us a lot more tools to work with when I'm working with polynomials. So let me look at another example that involves this idea. Let's say that we have f of x equals x to the fourth minus 4x to the third plus 12x squared plus 4x minus 13. And 2 plus 3i we know that 2 plus 3i is a 0. Problem tells us to find the rest. So we have 1, 0. How many more do we have to find? 3. One of them's easy. What's the easy one? 2 minus 3i. Oops, not z, 2. How does this help us? We have two complex zeros. What else could I do? I have several things I could do. I actually have quite a few things we could do. What do you think, Mary? Okay, so we could use Descartes' rule of signs to tell us about the positive and negative real zeros. And Descartes' rule of signs says we have one negative real zero. So that helps us out. How could we go about finding that one negative real zero? P and Q, right? So not too bad here. P is negative 13 and Q is 1. So what are our possible rational zeros? Plus or minus 1 and plus or minus 13. So that's not too bad to test with the P's and the Q's. So I could do synthetic division. I could plug in plus or minus 1 to test. The difficult thing with the P's and the Q's is it would be hard to do synthetic division with plus and minus 13. That wouldn't be too bad. So we could do our P's and Q's and do synthetic division, look for a zero remainder. So that's one way. That's our kind of tried and true method. Is there another way? Does someone else see another way? Well, you know these are zeros. Can't you do synthetic division with a zero and get a zero remainder? We could do synthetic division with these complex numbers. We're just multiplying by a real number and adding. So that's a possibility. You could do synthetic division with one of these zeros and get your answer and reduce the power of this by 1. Do synthetic division with the other complex zero and reduce the power by 1 again, and then end up with a quadratic that you could either factor or use the quadratic formula. So any of those ways would work. The P and the Q at this point is probably, because the numbers are pretty easy, is probably the easiest. But there's one more way. I know that x minus 2 plus 3i and x minus 2 minus 3i are both factors. So when I multiply these two together, what I'm left with also has to be a factor of this polynomial. So I can FOIL this out. It's not hard to FOIL this out. I get, just multiply this x, multiply these together. It's not a difficult process. We know how to do the multiplication with our complex numbers. When I FOIL this out, I end up with x squared minus 4x plus 13. Well, since both of these are factors, this has to be a factor of this. So when I divide this polynomial by this polynomial, I have to get a remainder of 0. When I divide a 4th degree polynomial by a 2nd degree polynomial, I'm left with a 2nd degree polynomial. So I would write x squared minus 4x plus 13, x to the 4th minus 4x third plus 12x squared plus 4x minus 13. Do the long division. I have to use long division here because I have three-term polynomial. Do the synthetic division, and then look for the roots of whatever I'm left with when I do synthetic division. Or sorry, when I do long division. Turns out that this comes out to be x squared minus 1. And x equals plus or minus 1 are the other two zeros. So I think for this one, doing the synthetic, just testing plus and minus 1 using our P's and Q's would save us a lot of work. But we just talked about 4 different ways we could approach the problem and get to the same place. Questions? And this all hinges on the idea that the complex roots are in conjugate pairs. All right, I want to show you how to set up one more problem that shows up in your homework. So this is how we talked about several ways you could approach this problem. And I want to talk about how you would approach one other type of problem. We want to find a cubic polynomial with zeros of 3 and 2 minus the square root of 2i, and we want f of 1 equal to 6. So we have an additional thing going on. Well, cubic polynomial, how many zeros cubic polynomial have? 3. How many zeros do we know? 2, but we know we can figure out the third one, right? What's the third zero? 2 plus square root of 2i is also a 0. Now what do we do with this f of 1 equals 6? I'm going to write out my polynomial. But because of this f of 1 equals 6, what we have to do is we can say there might be some number that we could factor out of the entire polynomial, a. Just like we did when we wrote our quadratic polynomial in standard form. We have that a out front. We're going to do the same thing. A, because we could have some number multiplying everything. A times x minus 3. Then I'm going to write out my factors. X minus 2 minus the square root of 2i. And x, whoops, one more parentheses, x minus 2 plus the square root of 2i. So those are my factors. Tells me f of 1 equals 6. So 6 equals a times 1 minus 3. I'm plugging in 1. 1 minus 2 minus square root of 2i. 1 minus 2 plus square root of 2i. And solve for a. So I just do this arithmetic. Here I'm just multiplying these out. And this equals 6. When I plug in 1 for x, I have to get 6 out of my function. So I'm just solving for a. We did this exact same kind of problem with quadratic polynomials. We had where we solve for a out in front. We could have this factor out. All right, questions on that problem? They all hinge on the roots, complex roots being complex conjugates. All right. So this homework will be due on block day. I'm not going to collect homework tomorrow. All we're doing tomorrow is the quiz. EOO every other odd. And 55 is written on the board. I'm skipping 55. All right, there you go.